Hello. For today, Data Communications and Networks 1 class, we will go to lecture 7, okay, which is chapter 4, Data Encoding. Part 1 is digital data to digital signals. There are actually 4 parts in this chapter: digital data to digital signal, digital data to analog signal to digital data, and analog signal to analog data to digital signal and analog data to analog signal. Okay, so there are 4 of them, but today we will talk about the first one. When you have digital data, how do you convert to digital signal? Okay, there are several encoding techniques that we can encode the digital data to construct a digital signal. Okay, so we have to compare, okay, between them. So how should we? What is the topic, okay, that we should evaluate their performance? The first one is the signal spectrum. Okay, the coding, okay, techniques that give good characteristics should have the signal spectrum that lack of high frequency components, because this will make it require less bandwidth, okay, and also doesn't have a DC component. Let's see what it means, okay, this one. So if you have a signal like this, or a signal like this is frequency domain, okay, or a signal like this, okay, and a signal like this. Or a signal like this. Okay, this one is this one has a high frequency component. Okay, so you have to keep like this part. This means the bandwidth is from this to this. Okay, this is the bandwidth, and this is also not very good because the power, okay, is at the edge of the bandwidth. So maybe you have to give, more bandwidth than wider bandwidth, okay, than the spectrum, because they have some. So because you don't want this one to be at the boundary, okay, it will spill over to the other side, to the other channel, okay. This one is good, okay. This one is also good. But usually when you do digital signal, usually when you send, okay, if you send wireless, usually you have to mod to some carrier, okay. So so this one is usually what we use. This one is what we use when you are sending baseband, okay. But this one is the one that is modulated signal, okay. So we use this one more when you actually send the signal through the wireless channel, okay. So this one is not good, okay. This one we don't like. Oh, okay, so we don't have okay, the lack of DC component, so that we can do the AC coupling, okay, via transformer, so that we can have electrical isolation and have less interference. So this is the DC, okay, 0 Hertz. This is DC. So this one we don't like. We don't like that it have the DC, okay. This one doesn't have DC, so it's good. No DC, okay. Again, what we are usually sending is the one that is modulated signal. Okay. Now the other characteristic is that the power should concentrate in the middle of the bandwidth. This is similar to what I was just showing you, okay. This is the middle of the bandwidth, okay. This is the middle of the bandwidth. So we want the power to be around, this is, suppose this is the bandwidth, okay. We want the power to be a lot around the middle of the bandwidth, okay? We don't want it to be at the edge because in this case, we have to give more bandwidth than necessary. Another property is the clocking property, okay? This is for synchronization. If you want to, you have to determine the beginning and the end of the bit position, okay, to do synchronization. So it's good if the coding that you are doing can give you the information on the synchronization. Okay. The next characteristic is the error detection. So good techniques to give you some error detection capability that is built into the physical layer. When you look at it, you know that, oh, this is wrong, this is not possible to happen, something like that, okay? And we will see when we look at the different line coding techniques. The noise immunity, we want it to be high, okay? The higher, the better. And the cost and the complexity, so usually they go together, okay? If it's good, usually it's complex and it costs more. So sometimes you have to trade off between the easy techniques and the more complicated techniques, okay, with the cost that you have to pay. The digital data to digital signal encoding techniques are sometimes called line coding. Okay, line coding is the same as the topic that we are talking now. The first one is NRCL, non-return to zero level. Okay. Okay. NRCI is non-return to zero inverted. Okay. And bipolar AMI, Pseudo Ternary, Manchester, and Differential Manchester. These are all the techniques that we will talk about in this lecture. For NRCL, you see that you have the same, the same voltage, okay, a constant voltage for each of the bit, period. Okay. In this case, the 0 is represented by high voltage. It's okay, to represent 0 by a high voltage or a low voltage. Depend on what do you agree upon with from the transmitter and the receiver. In this case, the 0 is represented by high voltage and 1 is represented by low voltage. For NRCI, you can see that the value of the bit, okay, it's not like high is 0 or low is 0, okay. It depends on the changing, okay, between 0 to 1 or 1 to 0 or 0 to 0 to 0, something like that. So we'll look at this in more detail. Bipolar AMI, this one has three levels. You can see that that's high and 0 level and then negative value or low level. Okay, so positive, 0 and negative values. Pseudo Ternary is the opposite of bipolar AMI. Okay, for bipolar AMI, the 1 is high, okay, high and low, and 0 is constant at 0 level. But Pseudo Ternary, when you get bit 0 is high and low, but bit 1 is a constant 0 level. Manchester and Differential Manchester, you can see that it changed a lot, okay. There's always a transition in the middle of the bit period. And we'll look at all of this in more detail here. The first one, NRC, non-return to 0, okay. There are two cases, the NRCL and NRCI. The bandwidth of this, you can see that most of the main lobe, okay, is from the 1 unit, okay, normalized from 0 to 1, and there's a little lobe, okay, from 1 to 2. This is considered also good in terms of bandwidth, but it has DC component, okay, because at 0 Hz, that has value, so it's not good in that sense. Okay. So NRCL used two different voltage levels to represent binary 1 and 0, as I had just said before. But NRCI, non-return to 0 inverted, This one use the present and absence of a signal transition at the beginning of the bit time. Okay, so check whether there is a transition at the beginning of the bit or there is no transition at the beginning of the bit. Okay, if there is a transition at the beginning of the bit, it means binary 1. If there is no transition, it means binary 0. So you can see here, okay, on the second graph here. So if it's 0, at first, okay, it's 0. If suppose it's high. If the next bit is 1, then they have to have transition. So it changed from high to low. Then the next bit is 0. If the next bit is 0, then there is no transition. So if it is low, it will keep being low. Then the next bit is 0, so it keep being low. Okay. Then the next bit is 1, so it have a transition from 0 to 1. The next bit is 1, so low. Okay. So it have a transition from high to low. Okay. Previously it's from low to high. Okay. This one is from high to low. And 1 again, so it's low to high. And then 0, so it keeps the same level. Okay. So you can see that the changing tell you that this is bit 0 or 1. Okay. This is an example of a differential encoding, which means that the value, the absolute value of the bit period does not represent whether it's a 1 or a 0, but the transition at the beginning represent the value 1 and 0. Okay. So differential encoding means that the signal is decoded by comparing. So it's encoded that way, so it's also decoded that way. Okay. By comparing the polarity of adjacent signal elements rather than determining the absolute value of a signal element. Okay. So this is good because it's independent to the polarity of the signal, and it's okay if the polarity is lost, which means that you don't know whether high is 1 or high is 0. You don't know, but you check the transition. Okay. And when you have noise, an RCI may be more reliable than an RCL because it detects the transition. Okay. And does not compare the value to a threshold. So if you see the transition, it's usually okay. Okay, let's look at this. Suppose you send this. Okay. Okay, now let's decode. Okay. Suppose at first you start here. So if you want to decode this, there is a transition here. Okay. So this is bit 1. There is a transition here, so this is bit 1. There is a transition here, so this is bit 1. There is no transition here, so this is bit 0. There is a transition here, so this is bit 1. If there is no transition here, this is 0. Okay, so this is an RCI. Okay. Now, if there's something wrong, there's noise. Okay, and make this look like this. Okay, make this look. If you want, and if you do an RCI, you will still see the transition. Okay, there's transition here, here, no transition here, transition here, no transition here. But if you use the NRCL, okay, what happens is that you have a threshold here. You have a threshold here. Okay. To tell you whether this is 1 or 0. Okay. Let's look at another example. Suppose I have this. Okay, like this. But this is NRCL. Okay. So this is 0, 1, 0, 0, 1. Okay. Now. Okay, suppose this is what I receive, and I have a threshold here. Okay, so what do I get? I get 0, 0, 0, 0, 0. Oh, sorry. Sorry, this is below threshold. Above threshold is 0. Lower than threshold is 1. So this is 1, 1, 1, 1, 1. Okay, which is wrong. Okay, so if you have something like this, but you can see that the transition is still there. So you use NRC NRC-IUB okay for this, but maybe not okay for this. Okay. Characteristic of both the NRC codes in general is that it's the most common, okay, and the easiest method. And the voltage level is constant during a bit interval. There are no transition. That's why it's called non-return to zero. During the interval, during the bit interval, there is no transition. And it's used the efficient use of bandwidth, okay, like 1 unit. You can look at this. Okay. You can see that the spectrum of the NRCI and NRCL has DC component, okay, at 0 hertz, okay. So at the y-axis here you have, so they have the DC component, and also the lobe is up to 1 unit, okay. The normalized frequency is 1.0 over here for the main lobe, but for the, if you include the side lobe, you also have the about 1.8 unit, okay. We consider the NRCI and NRCL to have good bandwidth, okay, because when you consider it in terms of bandwidth, usually we consider only the main lobe. So we will see that it is the bandwidth is comparable to the BSCH and HDB3 here, okay, which is also 1 unit of the bandwidth, okay, by considering only the main lobe. Now we will go back to the multi-level binary. For the multi-level binary, it means that we have more than 2 levels, okay, to represent 1 bit. Our bit has values only 0 and 1, but we use more, so we can represent it with only 2 values, right? 5 volts and 0 volt. However, in this encoding, we use 3 levels, okay, to represent them. There are 2 techniques. The first one is AMI, or bipolar AMI. The other one is called the Pseudo Ternary, okay? They are opposite of each other. For the AMI, when it's 0, when the bit is 0, you send nothing. When the bit is 1, you send high voltage, okay, or low voltage. So you have, you see that you have, when the bit is 0, you send nothing, okay. When the bit is 1, at first you have the plus, okay. For example, 5 volt plus 5 volt. For the next one, okay, you have the next bit 1, you have minus 5 volt, for example, like the minus voltage, okay, and then 0, sending nothing. For the pseudo ternary, it's opposite. When you're sending 1, okay, you send nothing, okay, the voltage is 0, you send nothing, and if the bit is 0, then you send plus or minus voltage, okay. So this one you can see that when it's 0, for pseudo ternary you send, for example, plus 5 volt. For the next 0, you send minus 5 volt. For the next one, you send plus 5 volt. So you alternate, okay, between plus and minus voltage, okay, for 0 bits. The bandwidth, you can see that it have 1 unit, okay. So it's good bandwidth. And also the spectrum center in the middle of the bandwidth, okay. So you see that this is good characteristic because at the boundary of the bandwidth, okay, they have only very 0 or very low spectrum, okay. This means that it will not interfere with the other signals. So for the bipolar AMI, the alternate mark inversion, okay, we have the advantage is that there is no loss of synchronization if you send a long string of 1, because you will have alternate plus minus, okay. However, if you send long string of zeros, it still have a problem because you send nothing for a long time, okay. So in this case, you can insert additional bit to force the transition of the signal, or you can scramble the data. And we will see the technique for scrambling the data in a little bit, okay. In this case, we will see that at the 0 hertz, there is no values of no spectrum power at 0 Hertz, okay, which means that they have no direct current or no DC component. And it uses less bandwidth. If you consider the whole bandwidth, okay, the main lobe and the side lobe of the NRC, you will see that AMI use less bandwidth than NRC, okay. And this will provide a simple means of error detection, okay, by checking the violation of the pattern. So you see plus and then plus voltage and then plus voltage again. There must be something wrong. So if you agree that you use AMI and you see plus voltage, and then the next one it have to be it have to be plus and then the minus and then plus and then minus, right? So if you have plus, 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 something like this, you know that something is wrong. So this is a kind of a built-in error detection, okay? The disadvantage is that it's less efficient than NRC coding in terms of the number of levels that you are using, okay? Because you can use 2 levels, okay, to represent a bit, which we can calculate by log base 2 of 2 equal to 1. So the number of level is log base 2 of L. L is the number of level, so it's equal to 1 bit. So 2 levels can represent 1 bit. But if you have 3 levels, okay, log base 2 of 3 is equal to 1.58 bits. So you should be able to represent 1.58 bits, but you represent only 1 bit, okay? So this is not efficient. Let's say k equal to log base 2 of L, where L is the number of the signal levels and k is the number of bits, okay? So in this case, you need 3 dB more power, more signal power than the NRC, because you want it to be separate, okay? If you look at this, NRC, you can, for NRC, you can have 0 volt and 5 volt, right? So you have a difference of 5 volt here. But if you use AMI and you have 3 levels, okay? So you use plus 5 volt minus 5 volt, so that the difference is 5 volt, okay, between the next level. But you see that the total here is 10 volt that you have to use, okay, from minus 5 to plus 5. This means that to have the same separation here, it intuition that you have to use more power, okay? You have to use higher amplitude, total amplitude, okay, or higher power to represent AMI than NRC, so that you can differentiate between the 2 adjacent levels, okay, of the signals. So that's why you need more signal power than NRC. Okay, because the receiver has to distinguish between the levels, okay, A plus A minus A and 0. If you use AMI and you have from 0 volt to 5 volt, okay, you will get something like this. Let's say 2.5 and minus 2.5, okay? So you have a total of 5 volt. But the difference between the 2 levels is only 2.5 volt, okay, which is not as good as this one. Next, we look at the pseudo ternary, okay? This is the same as AMI. As I said, it's just alternate it just represent it oppositely, okay? So the pseudo ternary has the same spectrum as the AMI. The next one is biphase. For biphase, we have 2 techniques, okay, in this lecture. The first one is called Manchester, another one is called differential Manchester. For Manchester, you fix, okay, that 0 is represented by high voltage change to low voltage, okay, so high to low, and the bit 1 is from low to high, okay. So in this case, you have, if it's a 0, it's low to high. If it's 1, if it's 0, it's high to low. If it's 1, it's low to high. 0 is high to low, low to high, low to high. Okay, so this is how to represent the Manchester. You just put the value of high to low, low to high, to represent bit 0 or bit 1. However, for the differential Manchester, you have, this is a differential encoding, okay? So you have to check the transition at the beginning of the bit. So if there is no transition or no inversion of the value, okay, the next bit will be 1. But if there is an inversion, okay, the next bit is 0. So in this case, if we start with high voltage, okay, and that's a change, okay, the first bit, you can see that there is a change from 0 to, there is a change from 0 to 1. Let me show you this. Can you see that this starts with a high, okay? And there is a change here, so it means that this bit is 0. And then over here, there is no change at the transition, so this bit is 1. There is a change, bit is 0. There's a change, bit is 0. There's no change, which is 1. There's no change, is 1. Okay, this is the same as what is over here. Okay, so this is how you look at it. You can see that for the Manchester and differential Manchester, okay, you will have the transition in the middle of the bit always, okay, because you change from low to high or from high to low inside of the bit. So you always have the transition in the middle, okay, whether you have a transition at the end of the bit or the beginning of the bit or not, but in the middle you always have them, okay. So it's good that you have synchronization. You will never lose synchronization in this case because you can track the transition in the middle of each bit. However, you can see that the baud rate is very high, okay, because you change very quickly. Inside of one bit, you must change at least once, okay. So it change much more frequent, okay, than the NRC or than the AMI. And therefore, you need more bandwidth in this case. Okay, so you can look at it this. You can look at it like this. Okay. This one is for NRC, okay? NRC you have, for example, in 1 second you send 4 pulses, okay? Because okay, to represent the NRC, okay? But for the Manchester you have to send as double that, okay? So you have like 8 pulses per second, for example. So it's twice as much. The max baud rate of the Manchester is twice as much as the max baud rate of the NRC. So you have more bandwidth, okay? You have to use more bandwidth in this case. So you can see that the bandwidth here is more, okay? Because the NRC has, in terms of the main load only, okay? In terms of the main load only, the NRC use only up to 1.0, okay? But for this case, you cannot cut at 1, okay? You have to use more. The Manchester require more bandwidth, okay? When you consider NRC only the main load. So the transition at the middle of each bit, this will help with the clocking mechanism, okay? And also for Manchester, it also tells you the data. But for the differential Manchester, the mid-bit transition will use for clocking only. Okay? And the Manchester is the standard of the IEEE 802.3 for baseband coaxial cable and twisted pair, okay? And CSMA CD bus, which is the bus LAN, okay? Anyway, the CSMA CD is what we're gonna study later. Is carrier sense multiple access with collision, okay, detection. Okay, so this is a technique, okay, that we use in the bus LAN, okay, or we use it in the Ethernet, okay. So we'll use this in LAN, which we will talk about in the later chapters. Okay. Anyway, but this is just to tell you that there is applications for this. The differential Manchester also have applications for the LAN, okay, which is the IEEE 802.5 tokening LAN, okay, that use shielded twisted pair. So this is standard for LAN. We use the Manchester for LAN because LAN is local area network, right? So it send for short distance because you use more bandwidth and you send, so you don't want to send for long distance, okay? Because you will use a lot of resource. So this one is used for local area network or for short distance. Again, this is the good thing about the biphase is that it's a self-clocking code because so it never lost synchronization, okay? There's no DC component and they have error detection. Okay. Noise will invert both the signal before and after, okay, to expect and after the expect transition to cause an undetected error. So it's very difficult, okay, for the AMI to have errors. Okay, because if you send like this, okay, you send like this, and then you receive, if you receive something like this, you see that there is no transition in the middle, okay? You receive some signal that there is no transition in the middle, but you say that the technique is Manchester, so there must be something wrong. It must be the noise make some of this change to the other values, okay? So to have no problems, to have undetected error, okay, that there is error but you don't know. The noise have to change the transmitted values from high to low and low to high, okay. They must have the receiver have to detect the transition in order for it to think that is correct, okay, so that it will not detect the error, okay. So if this one, okay, you have noise that change it, okay, the values to all low, okay, with no transition here, the receiver will know that something is wrong, okay, so it checked, okay, it detected the error. As I said before, there's a disadvantage of the biphase that it uses more bandwidth, okay, than the NRC and the max baud rate as the 4 pulse per second and the 8 pulse per second examples, that the max baud rate is twice that of NRC and require high signaling rate, okay, relative to the data rate. Because you send, for every bit you have to change once, okay? So it's not good for long distance application. And if you want to send for long distance, okay, you should scramble the data instead of using biphase. So biphase we use for short distance. And scrambling data technique, okay, we use for long distance. This is the spectral density of various signal encoding schemes. As I showed you before, you have NRCI and NRCL, which usually we consider only the main lobe bandwidth, okay, which is 1 unit. And then you have AMI and pseudo ternary, which is a good. The AMI and the pseudo ternary is a good. This one is AMI and pseudo ternary, okay, so it's a good shape here, okay. And then you have the Manchester and biphase, and differential Manchester, which is biphase. It's a solid line here, okay, so you have that is longer than the other. Again, we usually don't consider the lobe of the second, the side lobe, okay, of the NRC. So we consider NRC to have only 1 unit. So this bandwidth is the same as the AMI pseudo ternary, and the other one that we will talk about is BACH or HDB3. This one has a very good shape of the bandwidth with the only 1 unit, and the spectrum is mostly at the center, okay, with a no DC component. So we look at that. This is a BACH or HDB3 and HDB3, okay. They have both have the similar spectrum. BACH is a bipolar with S0 substitution. HDB3 is a high density bipolar 3 zeros Okay, we'll look at how to do the scabbling techniques, these two scabbling techniques. Okay. In this case, we want it to have no distinct component. Okay, and we have it to don't have a long sequence of zero level line signals so that you will not lose the synchronization. We don't want reduction in the data rate. Okay. And we also want the error detection capability. So what should we do? And if we have all that, it will be suitable for the high data rate transmission. Okay, what should we do? Okay, the first one is VACH, CS. Okay, this one is similar to the bipolar AMI. Okay, except that any string of A0s is replaced by a string with two code violations. Okay, so this will help. Okay, that when you have A0s, instead of loss, if you have a long sequence of zero, instead of having a zero level line for a long time, you will replace it. Okay, you will send something else. Okay, so that you have some like clocking information. But what you send cannot be the data. Okay, because if it's valid data, the receiver will misunderstand. So what the receiver do is that it have to use it as the code violation. Okay, so suppose the previous level is positive. You can see here the previous level is positive here. Okay, this one is positive. This bit one is positive. Then you represent the A0s by 0, 0, 0, which is all zero level line. And then one code violation. If the first previous one is high voltage, okay, or plus voltage, okay, or positive voltage, this one also have to be positive voltage, okay. So 0, 0, 0 violation. And then bipolar bit means that it just follow the normal bipolar, which means that if the previous one is positive pulse, then at this point it have to be negative pulse. So it's 0, 0, 0 violation, bipolar, and then 0 again, and then violation. Okay, violation means that you have the same polar. Okay, if it's negative before, you have to do also negative, which is violate the rule of the AMI that you have to alternate between positive and negative. Okay, so violation and then bipolar. So this is how you represent the A0s, okay, a string of A0s, if the previous level is positive. Now, if the previous level is negative, what do you do? Okay, so the previous one is negative before you got the A0s, right? So you have 0, 0, 0 violation. It's the same pattern that you have 0, 0, 0 violation, bipolar, 0 violation, bipolar. However, the waveform looks different, okay? Because the first violation has to be negative because the previous pulse was negative. So it has to be negative. And then the bipolar will be positive. Then the next violation is positive. And the last bipolar is negative, okay? So this is how you represent the BACH. If you look at this, okay, just look at this. Okay, you have 1, 1, and then 0 A0s, and then another A0s, and 1, 0, 1. Okay. Now, if it's AMI, what should you do? AMI is like this: 1 plus minus. Okay, positive, negative pulse, and then all 0 line, and then plus, minus, plus, something like this. So you have a long sequence of all 0 line, also 0 voltage. For BACH, what you have is that if it's positive, negative, right? So this previous one is negative. So you have 0, 0, 0 violation. Violation have to be negative. So it's going to be 0, 0, 0 violation, bipolar, 0 violation, bipolar. Okay? Then you get this one is to be, again, negative. Okay, negative. So you have 0, 0, 0 violation. Okay, it's the same pattern. Violation would be this is negative. This have to be negative. Okay, and then bipolar, which is alternate. Okay, negative then positive. 0 again, violation, positive and positive. Okay, and then bipolar, which is negative. Then it's 1, 0, 1. So if this one is negative, then this one minus will have to be plus, right? And then 0 and then minus again. So this is how you represent, you encode the sequence of this data sequence, okay, with the BACS encoding, which is a scrambling technique based on AMI with 2 code violations for a string of 8 zeros. The next one is HDB3, okay? In this case, sometimes, okay, they don't want even 8 bit of zeros, okay? They want to represent only with a 4 bit of zeros. In this case, you have 2 cases, okay, of the pattern to represent. It depends on the number of ones before the substitution, okay? So if the number of ones before substitution is even, so you have 2 ones coming here. If the number of ones is 2, so it's an even number, then you will represent the 4 zeros with bipolar 0, 0 violation, okay? However, if the number of ones, okay, since the last substitution here, you have only one of the bit 1, so one of the bit 1, so it's an odd number, okay? So if it's an odd number, since the last substitution, you will represent with 0, 0, 0 violation, okay? We do this because we want the DC to be 0, okay? We want to have no DC component. For the third substitution, you see that there is no bit 1 in between, okay? So it's considered as an even number of bit 1. So we represent with bipolar 0, 0 violation, okay? So this is how you encode with the HDB3, okay? Okay. This is 2, 1, okay? So it's considered even, you use bipolar 0, 0 violation, okay? Then this is only one bit of 1, so it's odd number. Counting from here, okay? Counting from here, this is only 1 bit of 1, so it's considered an odd number. Then you represent with 0, 0, 0 violation, okay? Then this is even number of 1 because there is no 1 here. So you count from here. How many ones between the last substitution? There is no bit ones, okay? So it's considered as even. So represent is bipolar 0, 0 violation, okay? So there is 2 cases to represent. If you compare these 2 together, okay, you will see that for the case that you have short, like fewer than 8 bits of zeros, okay? The BSA will not substitute, but HDB3 will always substitute. This is the case that compare MI, BACH, and HDB3, okay? Again, for the BACH, we always represent 8 bits of zeros, okay? With 0, 0, 0 violation, bipolar, 0 violation, bipolar, okay? And depend on the bit 1 previous than to the substitution with a 0. If it's minus or plus voltage, okay? So to have the waveform. The HDB3, similar to what we talked about, but it's 4, okay? Only 4 bits of zeros, and you substitute once. This is the probability of bit error, okay, in theory, okay, for in comparison between the NRC biphase, okay, is this line. The lower line is the NRC and biphase, and the upper line is the AMI pseudo ternary, ASK, oh sorry, we haven't talked about ASK and FSK yet. Just compare between NRC biphase, okay, which is the same probability of bit error, compared with the AMI pseudo ternary. You can see that with the same, okay, power, okay, you will see that AMI has a higher probability of error, okay. You can look at it like this. This one is AMI. Pseudo ternary is this line, the upper line. Okay. The lower line is NRC and biphase. So if you use the same, suppose you use the same EB. This is the power. Okay. So if you have this, you send the same power, because noise is the same. Okay. If you increase the power, you have the higher EB over N0. So with the same signal to noise ratio, okay, or the same power, transmitted power, you can see that the NRC and biphase is much better, okay. This is almost 2 magnitude better in terms of bit error rate, okay. However, if you want to have about the same probability of error or the same performance, okay, for NRC, you can use, for example, 8 dB, okay, for the EB over N0. But for the AMI and the pseudo ternary, you need to use about 11, okay, which is 3 dB more bandwidth, okay, to get the same performance, which is about 10 to the minus 4 bit error rate, okay. You see? So to have the same performance in the term of bit error rate, the AMI have to use higher, about 3 dB higher power than the NRC and biphase. And if you have the same transmitted power, the AMI pseudo ternary will have a higher probability of error or bit error than the NRC and biphase. Okay, this is the comparison that I want to show you. The next topic is the relationship between the data rate and the bit error rate. Okay. The data rate R is the total number of bits that can be transmitted in 1 second. So if you can, in 1 second, if you transmit 1 million bits, okay, so the data rate R is 1 megabit per sec. Okay, so the bit error is a probability, okay, that an error occurs in each bit. So if an error occurs with a 10 to the minus 4, it means that in every, so 10 to the minus 4, okay, it means that if the bit error rate, okay, so it means that this is 1 over, okay, 1 over 10,000, okay, so approximately 1 error in every 10,000 bit that you transmit, okay, approximately 1 error bit in every 10,000 bits that you transmit. Okay. Now, when you have an error, it means that you transmit a 1, but the receiver decides that it is a 0. Okay? Or if you transmit a 0, but the receiver thinks that it's a 1. Now, the bit error mainly depends on the parameter EB over N0, where EB is the energy per bit, and N0 is the noise power density per hertz. We can consider this as a signal to noise ratio in a bit. Okay? So if you know the signal to noise ratio or EB over N0 values, you can read the bit error rate from the graph here, depend on the encoding. So you can read it. Oh, okay. I have EB over N0 equal to 11 dB, and I use AMI, so the bit error rate is 10 to the minus 4, something like that. Okay. Now I want to show you the relationship between the data rate and the bit error rate. Okay. So let's look at it as the energy in 1 bit is equal to the signal power multiplied by the 1 bit duration. Okay, so EB equal to S multiplied by T sub B. And if you consider the unit, okay, of the variables, you can see that EB is joules. Okay, the unit is joule. S is the power is the unit is watt, and T sub B unit is second. Okay, so watt is equal to joules per second. Now the data rate is R equal to 1 over TB. What is that? Because TB is the bit duration, right? So suppose your bit duration is Suppose you send bit duration is equal to 1 microsecond, which is equal to 10 to the minus 6 seconds. This means that in 1 second, you can send how many? In 1 second, you can send 1 million bit, right? Because 1 bit is 1 microsecond, okay? So in 1 second, you can send 1 million bit. And therefore, I equal to t over 10 to the minus 6 equal to 10 to the 6 bit per second. Okay, so this is why the relationship is just this is t sub b, okay, but this is 6. It's different. Okay, now if we arrange, okay, and also the noise power density per hertz is n naught equal to k times t, okay? K is the Boltzmann constant and T is the temperature in Kelvin, in the unit Kelvin. So if we calculate this, EB over this one, okay, is equal to what? Is equal to EB equal to S multiplied by TB, okay, over N naught equal to S over R, right? Because TB is 1 over R over KT, right? So this is S over KT multiplied by 1 over R, right? Now, K is constant. T is also constant for that, that system, okay, that you are working on. And if the signal power, if you fix the signal power, this will also be constant. Okay, you will see that if signal to noise, if this one go up, it means that the data rate will be what? If this one go, these are all constant, right? So, so this one is the EB is the reverse, okay, of the R, of the 1 over R, okay. So if this go up, this also go up. So R go down, right? But if this go down, this one will go up, okay. Which means that if you have higher data rate, okay, the signal to noise ratio, okay, will decrease. So if you increase the data rate, the signal to noise ratio will decrease. When this one decreases, means that the probability of error, the bit error rate, okay, if this one go down, bit error rate will go up. Okay. So if you increase R and make the signal to noise ratio go down, then the bit error rate will go up, okay? So when you send with a higher data rate, okay, you have a higher bit error rate. So higher data rate, which means that higher bit error rate, okay, if the transmitted power is constant. But if you want it to, the bit error rate to be the same, so you increase R, but you want the bit error rate to be the same, means that you want EB over N0 to be the same. Then you have to increase the signal power, okay? If you increase R to double R, you have to double the signal power to make the ratio the same, okay? So that EB over N0 will be the same and the bit error rate will be the same. So this is what is the summary of this, okay? If R increase, bit error rate will also increase if the signal power remain constant. And so this is the end of this lecture. Okay, the next lecture will be about digital data to analog signal.